Hello, these are the exercises for section 5.5, the multiplication rule and conditional probability. The National Sleep Foundation conducted a survey on the number of hours of sleep per night that transportation workers get. The results are shown below. So here we have this table that has both row variables that are the amount of sleep per night, and we have these column variables which are the types of transportation workers that we have, okay? We have the totals for each of the columns down here, and the totals for all the rows down here, and we have a total of 795 individuals that were surveyed. All right, so let's answer this first probability question. What is the probability that a transportation worker gets less than 6 hours of sleep per night, given that it is a truck driver? So we have this word given, and that's going to tell us what to do. So we have the probability that we have less than 6 hours, given that we have a truck driver. So with that, you go through and find the number that are less than 6 hours and truck drivers, and we have this conditional probability here that says given it is a truck driver. So that means that the person that we are looking at has to be a truck driver. So this total that we're going to be looking at is going to be the number of truck drivers. Okay, so we have less than 6 hours and truck drivers there's 35 individuals out of the number of truck drivers, which is 203. This approximates to about 0.1724 or 17.24%. However, this ordering of this given, it makes a difference. So look at the next question. It says, what is the probability that a transportation worker is a truck driver given that they get less than 6 hours per night? So probability that we have a truck driver given we have less than 6 hours of sleep per night. So now you can see it. These two are conditional on different scenarios. So here we're still going to have the number less than 6 hours and truck drivers, but it's going to be out of this condition of less than 6 hours. So we have to be the number that's less than 6 hours. So we still have 35 individuals that are both truck drivers and less than 6 hours of sleep, but we look at the number that's less than 6, and we have 104 individuals. This approximates to 0.3365 or 33.65%. Part B. Use the contingency table to compute the probability that a randomly selected transportation worker is a pilot who gets less than 6 hours of sleep. Okay, so we want to know the probability that this person's a pilot who gets 6 to 8 hours of sleep. So it is also written as probability of pilot and 6 to 8 hours. Okay, we can go through and look at our table, because this is going to be the number of pilots and 6 to 8 hours out of the total number of people that we have surveyed. So we come up here and look at our table, and pilots that are 6 to 8 hours of sleep are 132. And the total that we've asked is 795. This is approximately equal to 0.1660. So you might have been thinking, wait a second, if this is an and probability, shouldn't we be doing a multiplication rule? And we can definitely do it doing the multiplication rule. Whenever we have a joint probability with and or with or, we can go through and utilize those rules that are appropriate for those situations. So when we have the probability of pilot and 6 to 8 hours, we have this and, so we have the multiplication rule that we have to use. And then we have to ask ourselves, are these two events independent or are they dependent? And that's not straightforward. So if it's not straightforward, you should assume that it is dependent because it will take care of both situations, okay? So when we use the general multiplication rule, we have the probability that we have a 6 to 8 hours, because that's this one of these events, and then we have the probability that we have a pilot given that we're only looking at 6 to 8 hours. So this is going to be the number of 6 to 8 hours over the total. Okay. So, and then we're going to multiply this by the probability that we are pilot given 6 to 8 hours. So we're going to have here the number of pilot and 6 to 8 hours over the number of our condition, which is 6 to 8 hours. Okay. So the number of individuals that we have 6 to 8 hours is 499. Out of our total, which was 795. Then we're going to have a number of pilot and 6 to 8 hours. Which is 132. Given that we have 6 to 8 hours. So you got to look at only those workers that get 6 to 8 hours of sleep. And we look up our table and we have a total of 499 workers who get 6 to 8 hours of sleep. Then we'll try those out. Those can cross out because they cancel out. If you didn't cross them out, that's fine. You can multiply across the top and across the bottom, and you'll get 132 over 795. When this is, you found the proportion for this, you similarly get the answer as above. Which is 0.1660. Okay. So in part C, what is the probability that two randomly selected transportation workers are both train operators if the selection is done without replacement? So here's a phrase without replacement that is indicative of something that's going to be dependent. Okay, so we have the probability that we have a train driver so that the and a train driver. Okay, so we look at our and we have multiplication, and this time we know it's going to be dependent, so we have to utilize this general multiplication rule. Okay, so it's probably that the first one that we choose is a train times probably that the second one that we choose is a train, given that the first one that we choose was a train. Okay, so we come up here and look at our table. There are 180 train operators. So this first one being chosen as a train operator, it's going to be 180 out of our total, which again is 795. However, when we take that first train operator and take them out of the pool, we now only have 794 left to choose from. And we only have 179 train operators to choose from. So we have 180 times 179. $32,220 divided by 795 times 794, because again, when you multiply fractions, you go across the top and across the bottom. So we have 631,230, so 631,230. And when you find that as a proportion, this is about 0.0510. So a little more practice with this without replacement examples. We're going to look at some probabilities that aren't from a table. They are just utilizing items. Okay. So a box contains 6 blue marbles, 5 red marbles, and 2 green marbles. If 2 marbles are randomly selected from the box, again, without replacement, that is the key phrase. What is the probability that both are blue? It's the probability that we have blue and blue. So again, we have our and probability. So we're going to use the multiplication rule. And because we have that replacement, we are dependent. So we have to utilize the general multiplication rule. So we have the probability that the first is blue times the probability that the second is blue, given that we already chose one and that first marble was blue. Okay, so this first one being chosen as blue, we have 6 blue marbles in our bag, and we have 6 plus 5 plus 2, 13 total marbles in our bag. Okay, after we choose that first blue marble, then it's only going to be 12 left in the bag. It's only going to be 5 blue marbles in the bag. So we have 30 over 156. And that is approximately equal to 0.1923. Here we have the probability that the first is blue and the second is green. Okay, again, we have an and. That's going to be a multiplication rule, and since we have this phrase without replacement, these are dependent events, and so we have to utilize the general multiplication rule. Probability that the first is blue times the probability the second is green, given that the first was blue. Okay, again, we have a total of 13 marbles in our bag, and we have 6 that are blue. So the probability of choosing the first blue is going to be 6 out of 13. Once we choose that, we keep it out of the bag, and we have 12 marbles total left in the bag. And how many of those 12 are green? Since we didn't choose green the first time, we're going to have 2. So this is going to be 12 out of 156. That's approximately equal to 0.0769. Then this part C is that the first is green and the second is blue. Again, we have our and, So we're gonna have to do a multiplication rule. And because of this phrase without replacement, we are dependent. So you have to use the general multiplication rule. Say the probability that the first is green times probability that the second was blue, given that the first was green. At the very beginning, we have 13 marbles, of which 2 are green. Then we take out one of the greens, and then we'll have 12 left over in the bag, and we will be left to choose potential of 6 blues. So again, we have 12 out of 156, which is 0.0769. All right, thank you.